Okay, so now we're going to do a navigation problem. Navigation problems tend to be a little confusing. It is really important that you draw a picture and you understand what's going on. So, our first navigation problem is we have an airplane flying in the direction of 30 degrees south of west. Notice that this isn't written exactly the same as the cardinal directions that we're used to. It's literally south of west. Um, at 600 miles an hour, and the wind is blowing in the direction of 60 degrees north of east at 40 miles per hour. Okay, so remember, this is north, this is east, this is south, and this is west. So it's very important that you have a picture. So if I go north of east, I'm going to go up from east, that would be my 60-degree angle. And then 30 degrees south of west, we find west and go downward, and that's going to be, it says 30 degrees, but if we're doing standard position, okay, we actually need to say it's 210 degrees. Okay, now the first thing we're going to do is we're just kind of going to go through the certain skills that we need. So we're going to find the component form for the airplane and the wind vectors. So let me change that really quick. So airplane, forgot the word plane. Okay, and then we're going to have to find the stuff that deals with ground. Okay, so again, referencing our angle, so we're going to do airplane. Okay, and remember your formula is your magnitude times cosine of your direction angle in standard position, and then magnitude or speed sine of your direction angle in your standard position. Okay, so let's tackle the airplane first. So we have 600 cosine of 210 degrees, and then 600 sine of 210 degrees. For our wind, we're going to use the same formula, magnitude, cosine of the direction angle. So we have 40 miles per hour, then cosine of 60 degrees. Now, north of east is already in standard position, so I didn't have to convert it. Okay, all right, so let's get our calculators out and figure out what that is. Okay, so 600 cosine 210, that is negative 519.6. Okay, and then 600 sine of 210. Is negative 300. And notice that when we find the component form of the vector, that does make sense because it is in the third quadrant. Okay, both of our components, our horizontal and vertical components, are negative, which places our vector in the third quadrant. So that's a good way to check if you're doing math right. Okay, let's do the wind. Okay, and then I get 20. And then 34.6. And those, again, your wind vector is in the first quadrant. Both of your components are positive, so that would put you in the first quadrant. Okay, so let's talk ground speed. Okay, so this is our first part. Okay, so ground speed is the direction, or excuse me, is the magnitude of the airplane plus the wind. Okay. Now, since we have the airplane and the wind in the component form, what we're going to do is we're just going to add those two together. So we're going to go airplane, which is negative 519.6, comma, negative 300, plus wind, 2034.6. Okay. So if we add those two together, that will give us the component form of our ground speed. So adding those together by components, we get negative 499.6 and negative 265. So since our components are both negative, that would again put our direction angle into that third quadrant. Okay. All right, now what we're going to do, since the ground speed is the magnitude, we're going to find the magnitude of our vector. So negative 499.6 squared plus negative 265.4 squared, and then remembering to take the square root. Okay, so here we go. All right, and I'm going to take the square root of that, and we get 565.72 miles per hour for our ground speed. Okay. All right. So that is our ground speed of our airplane. So that is what's happening relative to the ground. Okay. So now we're going to find our direction angle. We need to realize that it is in the third quadrant. Okay. So we're going to find the direction angle of our ground in the third quadrant. So we're going to take our component form. And we're going to apply our tangent formula. Now, since we're in that third quadrant, we might have to, okay, do a little adjusting. So tangent theta is equal to negative 265.4 divided by negative 499.6. If we use the inverse, okay. So tangent inverse 265.4 divided by 499.6. Okay, we get 27.9798 degrees. Okay, so the problem with that is that that's in the first quadrant. I want an angle in the third quadrant. Okay, so I want an angle somewhere in here. Okay, that's where it's going to line up. Okay, so I want my angle to be somewhere in here. Okay, so I'm going to have to add 180. Okay, so let's write ourselves a note. Since angle, or excuse me, vector, Okay, and if we add 180 degrees to that, that will put us in our third quadrant and give us a direction angle of 207.9 degrees. Okay? All right. So fourth part. We want to find the drift angle between the air and the ground. Okay. So let's see if I can get my lovely drawing. Okay. There we go. All right, so now, since we have this angle that or drawing that we can reference, okay, so this right here is your wind, this right here is ground, and this long one down below, that's our airplane. So we want to find the angle between the airplane and the ground. So we want to find this angle right here, okay? Whoops. Disappeared for a second. All right, whoa. Okay, so this angle, okay? So we know that this angle is at 210 in its standard position. Okay, we know that the ground angle is 207.98 in standard position. So what do you think we have to do to find that angle? Subtract. $210 and 207.98. So we will get 202. And that's it. Okay, I hope this was helpful. This was kind of a basic problem that kind of took you through kind of almost everything. They do get a little bit more complicated, like you will have to use law of sines and law of cosines and things like that. But I do hope this helped you. All right.